In this lesson, we'll continue our discussion of anatomy and physiology by taking a look at 6 basic life processes that we see in living organisms. We'll then take a look at the types of body fluids, and then we'll finish up with a very important concept in anatomy and physiology, and even in health and disease, homeostasis. So let's take a look at the basic life processes first. All living organisms have these characteristics that make us different from non-living organisms. The first one is known as metabolism, right? This is the sum of all the chemical processes that are happening in our body at one time. And that includes even catabolism and anabolism, right? So if you don't know what catabolism means, you can jot this down. Catabolism is chemical reactions involving breakdown, right? Chemical reactions involving breakdown. An example would be digestion, right? When we eat food, we're going to break it down to get energy. Anabolism involves chemical reactions that build up, right? We're going to build things, right? So chemical reactions that build up. Example, let's say we were going to build or make some proteins in our body, right? We need different proteins. There's proteins in the blood. There's hormones that are proteins. You may know collagen, right? Collagen in the skin is a protein. We have to make those proteins. So those would be anabolism, right? Or anabolic. Okay, so metabolism is all the chemical reactions that are happening in our body at one time. The second basic life process is responsiveness. Very simply, this is the ability, and it's usually the nervous system that's going to detect and respond to changes that are happening in the external environment, right? That's the environment around us. Maybe, just like a change in temperature or something like that. We respond to that. Or changes within our internal environment, what's happening inside of our organs, inside of our body fluid. So we have to respond to those changes, right? If the temperature outside keeps going up and up and up, we would overheat if we didn't respond to that. So we have to start sweating to cool down, as an example. Okay, and like I said, the nervous system is the predominant nervous system and endocrine system are the two systems that are really the responsive ones. The third basic life process is movement. So this includes motion of the whole body, right? Getting up out of bed, eating breakfast, going to school, going to work, right? That type of thing. You're moving your whole body. But it also includes movement of individual organs, right? If you think about your heart beating, it's moving. Your stomach, right, when it's digesting, is moving. So that would be an example of that. Single cells can move in certain instances. A good example here would be a white blood cell, right, moving around the body to fight infection, right, to fight the bad guys called pathogens, actually. And then even within a cell, specialized structures known as organelles can move inside the cell. Okay, and we'll talk about that when we look at cellular anatomy. All right, so metabolism, responsiveness, and movement. These are the first three of the basic life processes. The fourth one is going to be growth. So now this refers to an increase in the size and complexity. Now this could be due to an increase in the number of cells, right? When we have cellular division and we make more cells, or it could be the cell is just getting bigger, right? Or it could even be a combination of both, right? So that would be growth. Differentiation is just the specialization of cells. We have something like 75 trillion different cells in the body, right? They're not all the same in function, right? Muscle cells do muscle activity, nerve cells do nerve activity, blood cells do their activity. So they're all specialized. That is what we call differentiation or differentiated, right? So it's a great word for specialization. Finally, the last basic life process is reproduction. So this refers to either the formation of new cells, either for growth, right, as we grow up, for repair or replacement. So say cells were damaged or we lost cells. Let's say you go out and you get a sunburn and your skin peels, right? We got to replace them, so they're going to be replaced. Or it could be even the formation of a new little individual, right? Making a new baby. Okay, so growth, differentiation, and reproduction are the last three, right? Okay, let's switch over just a couple slides on body fluids. So, for body cells to survive, the composition of the surrounding fluids must be precisely maintained at all times. And that's something that you're going to study as you go on in anatomy and physiology, how we maintain those body fluids. So for this lesson, I want to define where these fluids are. There are two main categories you can highlight. The first one is known as intracellular fluid, right? Intra means within, cellular means cells, and we can abbreviate that ICF. A lot of our diagrams, even when I speak to you, I'll talk about the ICF. And guys, it's nothing more than the fluid inside the body cells. Now, the other category is the extracellular fluid. Extra in this case means outside the cells. And this we usually abbreviate the ECF, right? That's going to be the extracellular fluid, right? This is the fluid outside the body cells. Now, we can find that in basically two main categories, I guess. The first here, give this a highlight right here. The first category is going to be the interstitial fluid. Give this whole line a highlight, and then I'm going to go to the next slide. And the other one is going to be the extracellular fluid here. Just kind of highlight right there, and I'll explain what I mean by that. Okay, so again, like we said before, the intracellular fluid is the fluid inside the cell. Extra fluid is the fluid outside the cells. So one of the places we find fluid outside the cells is actually just around the cells, right? The fluid that would be around the cells. This fluid is known as interstitial fluid, intercellular fluid, or tissue fluid. Okay? Interstitial fluid, intercellular, or tissue are all the same, and that is just the fluid in the spaces between the cells, right? So this is the fluid around the cells. The rest of the extracellular fluid, and that's what I have here, extracellular fluid in addition, are located in the blood. So this would be the plasma, right? You probably know about plasma. This is the extracellular fluid we find in the blood vessels. And you may have heard of lymph. This is extracellular fluid within the lymphatic vessels. CSF stands for cerebrospinal fluid, right? Cerebrospinal fluid. Our brain and spinal cord are actually floating in water. That is extracellular fluid, right? Fluid outside the cells. So that is CSF, we abbreviate it. Believe it or not, within your joints, you have fluid. That is known as synovial fluid. And then even in your eyes, there is fluid known as vitreous humor. So again, these are all fluids that are outside the cell. That's why they are categorized as extracellular fluid. Okay. The last thing I want to talk to you about in this lesson is something known as homeostasis. So before we go over the slides, just kind of think about this for a minute. If I were to ask you, what's like a normal body temperature? And most of us would say, hey, you know what, 98.6. If I said to you, what's a normal blood pressure? Right, most people would say 120 over 80, right? So it's kind of a normal thing. But what happens if our body temperature starts to go up because it's hot outside, right? It's 98 degrees outside, you're working outside, your body temperature starts to go up. If we kept our body temperature going up and up, eventually we would have seizures and potentially could die from a heat stroke. So we can't have that. Things have to happen as your body temperature goes up. Things happen to bring the body temperature back down. You start to sweat. Right? You may notice your skin gets red because your blood vessels are dilating. They're opening up to release heat from the body. Okay, so your heart may start beating faster. You may breathe a little bit quicker. All these things work to lower your body temperature. Right? If we didn't do that, again, we would die. So in our body, we have this thing called homeostasis. This is a state of balance. Normal body temperature, 98.6. That is normal. That's a state of balance. 120 over 80 on the blood pressure is a state of balance. pH, which is acid-base balance, different ions like sodium, potassium, they all need to be at a certain level. Right? If they go up too high or too low, we become sick. So homeostasis is when all the body systems, and we know from a previous lesson there are 11 body systems, they work together to maintain a stable internal environment. Right? These systems, guys, respond to external, right, changes outside of our body, and internal changes, changes within our body, to keep variables within normal range, such as body temperature, fluid balance, if you want to add there, blood pressure, right, blood sugars. All these things need to be in a certain range, right? If we can't get blood pressure back down, we have hypertension, right? Or if we have like low blood pressure, we can't get it up, that would be hypotension. If we had blood sugars that are consistently too high, we can't get them back down to normal, we have diabetes. So homeostasis is an important concept. There's basically two methods that we regulate homeostasis, right? So homeostatic regulation is the adjustment of physiological systems to preserve homeostasis, right? So it's these changes that we make to maintain homeostasis, to do the balance. So there's basically two mechanisms. The first one is known as auto-regulation. Auto means self, right? Self-regulation. This is an automatic response in either a cell, a tissue, or an organ to some type of change. Right? So just let's say in a cell, something happens that goes out of, it's a little bit advanced, but something just goes out of alignment. The cell makes the correction itself to reestablish homeostasis. Or let's just say if you look at your right arm and for some reason, for whatever reason, there's not enough blood going into the right arm, the right arm will make adjustments to dilate the blood vessels, let's say, to bring more blood into the area, right? The arm kind of took care of itself, or the organ, right? So the structure, the cell, the tissue, or the organ are making the necessary corrections. That is known as autoregulation. However, if the nervous system or the endocrine system are called in to do the regulation, that we call extrinsic regulation. This is responses controlled by the nervous system and the endocrine system. Right? The nervous system is actually going to send out nerve impulse. Nerve impulse is known as action potentials, and the endocrine system puts out chemical messengers known as hormones. And these nervous systems action potentials and the hormones will reestablish homeostasis. All right. So extrinsic, the key is the nervous system and the endocrine systems are kicking in. So we have a couple components that are necessary to do this homeostatic regulation. The first component is known as a receptor. That's going to receive the stimulus. That's the thing, guys, that's going to sense some type of change. The receptor then is going to notify a control center, which basically processes the information coming from the receptor. The control center, if it thinks something needs to be done, is going to send a signal out to an effector, which carries out the instructions. So just as an example on you, and we'll look at this in a little bit more detail in a minute, just think about this. Let's say you're sitting at your desk and somebody was cold in the house and they turned the thermostat up really high. So you're sitting here, learning this material, and you realize, you're getting hotter and hotter. So there are receptors that are responding to heat in the room, right? The receptors are in your skin. So the receptor now fires in response to the room getting warm and your body getting warm, and it sends a signal to your brain. the brain is going to be the control center. And the brain says, hey, you know what? It is starting to get hot in the body. We're now like at 99 degrees, going up to 100 degrees body temperature. So the brain processed the information, or is processing the information that you're getting hot. So now the brain says, you know what, it's getting a little bit too dangerously hot inside the body. We got to do something about it. So it sends a signal out to your sweat glands, and it turns on your sweat glands and you start to sweat. Sweating is a cooling process. That should start to bring your body temperature down. The brain may also say to your blood vessels in your skin, you know what, open up, dilate. That will lose heat like a radiator from your body. And now body temperature comes down. So the sweat glands and the blood vessels were the effectors. They responded to the control center. I'll give you one more example just outside the body. In your house, you probably have smoke detectors, maybe a carbon monoxide detector, motion detectors, that type of thing. These would be the receptors. They're monitoring what's happening in your house. Let's just say somebody is cooking something on the stove and it starts to smoke up, right? They're burning something on the stove a little bit. So the receptor, the smoke detector, would fire and would send a signal to the alarm station somewhere, right? So you have Sloman's or whatever, one of these alarm stations, and they're going to be the control center. All right, they're going to process the signal. Hey, you know what? We have a smoke alarm going off at so and so Main Street, and we better do something about it because we are getting a signal that there's smoke in the house. So the control center now is going to call the effector, right? Probably since it's smoke, they're going to call the fire department, and they send the fire department, and the fire department comes, and if there was a fire, they put the fire out, or if there wasn't a fire, maybe they clear the smoke out, but they get things back to homeostasis. All right, so this is the same thing that happens in our body. All right, so these receptors, control centers, and the effectors, they limit the fluctuations. They kind of keep them close to a set point that we've established, right? The set point for body temperature is 98.6, right? The set point for blood pressure about, 120 over 80, that type of thing. All right, your room temperature, whatever you keep it at, 70 or 72, right? Whatever you keep your room temperature would be a set point for your inside your house, as an example. Okay, so receptor, control center, effector, right? We need these to do homeostatic regulation, right? Getting us back to homeostasis, this state of balance. So here's a picture that's pretty good. We're showing an example of controlling temperature in your house. So what you have, guys, here is homeostasis, which is normal room temperature, whatever you determine it's going to be, right? In this example here, they're setting the set point at 22 degrees centigrade, which is, or Celsius, I should say, which is about 71.5 degrees Fahrenheit, just about 72 degrees. So they're setting that as the temperature that you want to keep. So watch this, watch what happens. So let's just say the house is at normal room temperature. We'll say 72 degrees because it's easier. And let's just say it starts to get hot in the house. So temperature is going to start to go up. Maybe the sun is shining, your windows are closed, that type of thing, and the house starts to get warm. So now homeostasis is disturbed. It's getting too hot. So we said before, we need a receptor. So probably in your hallway, right, most people have in the hallway, there's a thermometer. That is the receptor. That is what is monitoring the temperature change. Once the temperature goes up in the thermometer, that's going to set a signal to the thermostat. Now the thermostat we have again at 72 degrees, right, 22 degrees centigrade. That's going to be the control center. So that's going to process the information coming in. Hey, you know what? The thermometer is telling me it's getting too hot. So now that would be considered the control center, right? That processed the information coming from the thermometer. Control center says, yep, it's getting too hot. What are we going to do? Let's turn on the air conditioner, right? So you have a central air, let's say. It sends a signal to your air conditioner turns on. The air conditioner is the effector. It responded to the control center. So what's going to happen when the air conditioner goes on, your room is going to start, or the house, right, temperature is going to start to go back down to normal. Okay, so that's an example of how the receptor, the control center, and the effector work together. Okay, and you'll see. Now we don't want the room to get too cold. Once it starts, the temperature starts to get too cold. The thermometer is going to say, hey, you know what? It's cool enough. Let the thermostat know, hey, we're at normal house temperature, and it will shut off the air conditioner. Right. So if you listen to your air conditioner all day, right, you hear it click on, and then it clicks off. A little bit later, it clicks on, and then it clicks off. And that's exactly what's happening. All right, so this is a great example of the receptor, the control center, and the effector in your house. Now, here's just another book, different, same idea though, right? You have a stimulus, changes a controlled condition, right? Temperature, let's say. The receptor picks up that change, sends a signal to the control center. Control center processes that information. That's its main job. And if it needs to do something, it's going to send a signal to the effectors, which are going to respond. Once they respond, things go back to normal. Homeostasis, right? That's the key. So there are two ways that we control homeostasis, get back to homeostasis. There's something known as negative feedback, if you want to give that a little highlight right there, and then a little bit further down on your page is positive feedback. Let's do negative feedback first. So this is the response of the effector that negates the stimulus, or if you want to put over the word negates, put down reverses the stimulus. All right, so whatever the change was, the stimulus, we're going to reverse it. All right, so the response of an effector reverses the stimulus, right? Whatever the effect of the stimulus was, and the body is brought back into homeostasis. We reestablish our normal range, and that was my example before of body temperature, and I think we're going to do that on one of the pictures here. But when your body temperature went up, you started to sweat, your skin turned red, maybe your heart beat a little bit faster, you breathed a little bit faster, and then your body temperature came back down. So the body temperature went up, but then we reversed it back down. Okay, that is negative feedback. Well, let's just say just the opposite. How about this? Say you went outside and it was 5 degrees out, and you had to run outside for a little bit and you didn't bring your coat. So now you're standing outside. Let's say there's an alarm, like a fire alarm or something like that, and you run out of the building. So now you're standing outside and it's 5 degrees. Your body temperature is going to go down. Right? So that's a change in your body temperature. That would be the stimulus. So probably your sweat glands are going to be turned off, right? You're not going to sweat when you're in a cold environment, but you may start to shake, right? You may start to shiver, which is going to produce heat from your muscles to bring your body temperature back up, right? So the stimulus was to have a low body temperature, but your body started to shiver to bring your body temperature back up. That is negative feedback. We reversed the stimulus. So here's an example. Again, it looks a little bit intimidating when you first look at this, but it's about body temperature here. So the normal body temperature we're going to say is about 37.2 to 36.7 degrees centigrade. It's about 98.6 would be the set point. That would be a 37 in the middle. Right? So 98.6 is the set point. So let's kind of go through this real quick. Watch this. So we have homeostasis, say 98.6. For some reason, your body temperature starts to go up. That's a disturbance in the homeostasis, right? That's going to be the stimulus. That's what's going to start this process. So in our skin and throughout our body, we have receptors that sense these changes in body temperature. They then send a signal to the brain. That is the control center. And the brain says, yep, it's getting too hot in the body. Let's do something about it. It sends a command out to the effectors. In this case, the blood vessels and your sweat glands. Right? We're kind of doing it simple. There's probably even more systems, but these are a good example. Blood vessels and the sweat glands. The blood vessels are going to dilate in your skin and move the blood to your skin so that you can lose the heat from your body like a radiator. Right? Have you ever been around somebody that's hot? You can just feel the heat coming off of them. Then The other effector was the sweat gland. That is going to produce sweating. So between flowing the blood to the skin and sweating, what's going to happen? The body temperature will come back down to normal. Okay, just the opposite. Say we're at normal body temperature and your body temperature goes down, right, below 98.6. So again, receptors throughout your body for temperature monitor or sense, hey, you know what? It's getting cold inside the body. Sends a signal to the brain. The brain says, hey, you know what? Yep, it's getting cold in here. We got to do something about it because it can be dangerous. And now it's going to go to the blood vessels and the sweat glands in the skin, but it's going to turn them off. You're not going to sweat. Your blood vessels in your skin are actually going to constrict. And that's why if you ever look at somebody that's cold, they look blue. That's because there's less blood in their skin and that gives a blue appearance. And the skeletal muscles are targeted also. And the skeletal muscles will be caused to shiver, right? They're going to contract to produce heat. The sweat glands are going to be turned off and less blood flow to the skin. Again, that's why you look blue. And these things here should start to bring your temperature back up. And we're back at 98.6. So both the top diagram up here, guys, and the bottom diagram represent negative feedback, right? In both circumstances, there was a change where we brought them back, right? We reversed it to homeostasis. That's a great picture. So take a look at that. Look at this a couple times just to make sure you get the hang of it. All right, again, here's just from another textbook kind of showing the same type of thing. So we have a stimulus, but this one's going to be blood pressure. So let's just say we have a change in the blood pressure. So there are receptors again in our body, like in blood vessels and things like that, that sense a change in pressure. So they would be the receptors. They send a signal to the brain. The brain is the control center. The brain says, hey, you know what? We have a high blood pressure, let's say. So it's going to tell the heart to stop beating quite as hard, which can lower the blood pressure. It may tell our blood vessels to dilate, which lowers the blood pressure, and then we end up going back to normal. Right? So that's a negative feedback also. Now, the second type of feedback we had said was positive feedback. So here we have a stimulus, right, some type of change, but instead of reversing the change, highlight right here, we amplify the change. We make the change more, right? And a great example of this is labor and delivery. When a woman gets that first labor contraction, negative feedback would make the contraction go away, and that would be bad. We would never have the baby. But what happens is you have that first contraction, and then the second one's a little bit stronger, and then the third one's a little bit stronger, and each contraction gets stronger and stronger and stronger until junior comes out. Okay, so here the initial stimulus was made stronger. It amplified so that we could speed up this process of having the baby. Again, had we had negative feedback, the contractions would have went away, right? And although a woman may want that, but in order to get the baby out, we have to have the contractions get a little bit stronger. The other example is clotting. When we start to, say we have a cut, we start the clotting process. If we had negative feedback would stop the clotting process and we would bleed to death. But what happens with clotting is once it starts, the process is actually sped up and made faster, and it just becomes like a big a snowball effect, bigger and bigger, and until the hole is sealed up. Because if clotting was a slow process or if it was reversed, again, we would have died years ago. We wouldn't be here. So labor and delivery, if you want to put down as an example, labor and clotting. And I have an example of clotting right here. So here they're showing you a blood vessel that was cut, severed, right, a little bit. Chemicals are released from the tissue that was damaged, and that starts the clotting process. Here you see some platelets start to fill the hole a little bit, and that seals that hole temporarily, and more chemicals are released that causes positive feedback, where this is going to happen faster and faster until we get a nice blood clot. Because again, if this was a slow process, we especially with a big cut, right, we would bleed and potentially die. Okay, so labor is a great example of positive feedback. Clotting, there are a bunch of other ones, but they're a little bit beyond the scope of the course of where we're at this level. So just know those two for me. And just another example. So here they're actually showing labor. So again, you have contractions in the wall of the uterus, and the contraction is going to start. The brain is going to get the signal from the receptors of the uterus, and now the brain is going to send out hormones. You guys may know of oxytocin. In medicine, sometimes women will get something called pitocin. That's kind of a synthetic hormone that causes stronger and stronger contractions. And eventually the contractions are so strong, again, that junior comes out, and then we're back to normal once the baby's out. Okay, last slide. So it's not just one system, if you notice, that does homeostasis. It's a bunch of systems, right? When we got hot, it was the integumentary system, which had the sweat glands. It was the cardiovascular system, which controlled the blood vessels. They worked together. And homeostasis is also a dynamic process. It doesn't just happen once during the day. It is continually happening throughout the day, sleeping, awake, right? It just doesn't happen once. It is constantly happening in response to changes that your body is going through. If our body cannot reestablish homeostasis, that state of balance, failure will result in disease. And if you want to even add, I hate putting it there, but even death, right? If we can't get that blood pressure back down, if we can't lower the blood sugars, right? If we can't, change acid-base balance in the body, right? Theoretically or potentially, we can die if we don't get help. Okay, so homeostasis is extremely important. Okay, so that concludes this lesson on homeostasis, our body fluids, and the basic life processes.